Jupiter is the solar system's security guard. Not on the list. Not getting in. That's not bravado. It's mass talking. With more than twice the material of all other planets combined, Jupiter owns the biggest gravitational handshake in the neighborhood. When wanderers drift through our foyer, icy centaurs from the outer reaches, long-period comets from deep storage, or a speedy interstellar guest, it's usually Jupiter who checks ID, decides whether to wave them through, spin them around, or escort them to the exit at escape velocity. Start with the basics of bouncer physics, cross-section and reach. Jupiter's "you will feel my presence" zone. Its Hill sphere is vast, giving it room to start shaping paths long before close approach. That reach is paired with gravitational focusing. Even objects that wouldn't have clipped a smaller world's sphere of influence get pulled inward toward a deeper pass. Come in slow, and the planet can curl you dramatically. Arrive fast, and you still feel the tug, but your path is more glance off the shoulder than bear hug. Interstellar visitors like 3I typically scream in with high excess speed, so the turn they experience is modest. But modest isn't zero, and a few degrees of re-aim near a heavyweight matter far downstream. Deflection is Jupiter's default move. Most inbound bodies leave with a reoriented orbit and a different energy budget relative to the Sun. If the body arrives prograde relative to Jupiter's motion and swings out aligned with the giant's path, it can leave faster, catapulted outward into a longer, lazier orbit, or straight out of the solar system. If it peels off against Jupiter's run, it can depart slower, dropping the perihelion sunward and making a future visit to the inner planets more likely. The planet pays for the change with a microscopic recoil in its own orbit, too small to matter to Jupiter, enormous to the newcomer. Bouncers don't get bruised by elbows. Capture is a rarer trick because gravity alone is stingy with handcuffs. Temporary satellite capture does happen. A small body stumbles into a configuration where for weeks to years it loops Jupiter before a subsequent nudge evicts it. Lasting capture usually demands energy loss on the way in, drag in an atmosphere, unsafe near Jupiter, tidal dissipation, minimal for small bodies, or a three-body trade where a binary object approaches and one member departs with extra energy while the other stays bound. Nature plays that game occasionally. The irregular moons, with their odd tilts and elongated tracks, testify to past winds. But for a fast interstellar comet, the window is narrow. The guest rarely lingers long enough for gravity alone to close the cuffs. Now, about that shield cliché. Jupiter both protects and provokes, and which role it plays depends on inventory and geometry. For some long-period comets, a timely deflection lifts peripelia away from the inner solar system, starving the impact risk for a while. For others, Jupiter's nudge drops them onto planet-crossing paths they never would have found on their own. Statistically, it reduces the number of frequent flyers that haunt Earth-like orbits for long spans, while creating short, sharp episodes when a few new arrivals dive inward. It's less a force field and more a customs checkpoint with a talent for rerouting traffic. The amplify or damp question for a 3I class interstellar visitor turns on speed and aim because an ISO arrives with a hefty hyperbolic excess. Jupiter's best party tricks are toned down. An amplifying scenario looks like this. The object approaches on a trajectory that lets Jupiter rotate its outbound path just enough to trim its heliocentric speed and lower its perihelion toward the Sun on the next pass. Result: brighter comet for a season, a photogenic show, maybe a closer look for inner system spacecraft. A damping scenario is simpler and more common. The giant tilts the ISO a few degrees the other way, raising its outbound energy and whisking it past the stage before anyone can tune a spectrograph. Either way, the change is almost entirely about the visitor. Jupiter's own state barely registers the exchange. Jupiter's mass also sets the tone for entire small body populations, which is why its bouncer resume runs longer than any one encounter. Centaurs, icy, unstable bodies wandering between the giant planets, live on borrowed time, because repeated distant nudges with Jupiter and Saturn walk them toward either ejection or transformation into short-period comets. The Trojan swarms co-orbiting with Jupiter at the stable L4 and L5 points reveal the flip side, the same gravity that flings can also corral, parking debris in long-lived niches. Meanwhile, resonances tied to Jupiter's period sculpt the main belt, carving out gaps and herding families of asteroids onto safer or sketchier trajectories over millions of years. The bouncer doesn't just bounce, it rearranges the furniture between shifts. If a visitor dives too deep, Jupiter adds environmental hazards to mechanical ones. The radiation belts are harsh enough to cook electronics. The upper atmosphere is a drag blanket that turns deep grazes into brief, spectacular plasma events. The ring system and small inner moons add debris risk on tight passes. Natural bodies don't file flight plans, so the occasional dramatic breakup or impact, think Showmaker Livy 9, is baked into the long-term statistics. It's a reminder that Jupiter doesn't only redirect traffic, it sometimes ends the journey. One subtle skill of the bouncer is timing. A nudge delivered when the visitor is near Jupiter's periapsis in the planet's frame yields the biggest redirection. For mission designers, that means targeting the aim point weeks in advance. For nature, it means a roll of celestial dice. Most ISOs don't show up with perfect timing. The ones that do become case studies in how even a small angle change near a heavyweight can redraw pages of the subsequent ephemeris. Put all that together, and Jupiter's role is clear. Not an impenetrable wall, not a chaos machine, but a high-leverage editor of trajectories. It suppresses some risks, concentrates others, and ensures that most interlopers never become long-term houseguests. For a flashy ISO like 3I, Jupiter is far more likely to hustle it along than to hand it a backstage pass. Next, we'll listen for the echoes in the wider crowd, how those nudges ripple through the asteroid belt and Kuiper belt, shifting resonances, altering shower rates, and leaving faint statistical fingerprints that only emerge when you count for decades. The belts are like wind chimes. Change the breeze, hear a new song, very softly. If the main asteroid belt and the Kuiper belt had weather forecasts, most days would read calm with a chance of whisper. Yet those whispers add up. A shift in resonance here, a distant nudge there, and the population statistics hum a slightly different tune years or decades later. No single rock makes headlines. The melody changes because thousands of small bodies adjust their orbits by a hair. It's background music you only notice after someone shows you the spectrogram. Start with the main belt, that broad arch of relics between Mars and Jupiter. It isn't a uniform gravel road, it's a quilt stitched from families, gaps, and slow migration lanes. The gaps, famous ones tied to simple period ratios with Jupiter, aren't empty for dramatic effect. They're where repeated gravitational timing pushes asteroids onto more eccentric or inclined paths. But the edges of these gaps are not brick walls, they're surf zones. A small body that drifts via thermal effects or gentle collisions can graze a resonance boundary and begin a random walk in orbital elements. The walk is slow, the consequences are cumulative, and the soundtrack is more rustle than crash. Resonance shifting is the quiet knob. When the phases of giant planets evolve, ever so slightly, the exact semi-major axis locations and widths of resonances breathe. We're not talking about moving furniture, we're fluffing cushions. Still, fluff enough cushions and some pebbles tumble off the couch. A resonance that puffs wider sweeps up a few more asteroids. One that contracts drops some back to safer sands. Over decades, the count of near-resonant objects on our survey lists responds with tiny upticks and downturns, like a tide gauge trying to decide whether the ocean is teasing it. The Kuiper belt plays a different tune, because Neptune is the conductor and the stage is bigger. Out there, resonant populations, 3-2 Plutonos, 2-1 Twide-Tunos, and a choir of higher-order harmonies, preserve early migration history, but they're not static dioramas. Orbital elements liberate within resonance cells, and chaotic layers border those cells like ragged coastlines. When subtle, long-period variations in Neptune's orbit shift the boundaries, particles perched on the lip can leak out, while others are captured as they drift under the slow press of tiny forces or gentle collisions. The net effect is a breathing reef. Individuals come and go, while the structure persists. What turns these rearrangements into something we might feel in the inner solar system is transport, and transport prefers corridors. In the main belt, a combination of slow semi-major axis drift and encounters with weak resonances can lift eccentricity enough to send an asteroid into Mars-crossing space. From there, statistics take the wheel. Some are ejected, some are ground down, and some become short-term Earth crossers before their tickets expire. The Kuiper Belt's outlet is farther and colder, but the principle rhymes. Objects leaking from resonant or scattered zones can migrate into the Centaur population, where repeated distant nudges with the giants remix their paths until a fraction turn into short-period comets. None of this produces a sudden comet blizzard. It's drizzle with personality. Could a transient visitor, say an interstellar comet streaking through, change the chime? Not by grabbing the whole wind chime and shaking it, but by altering phases at exactly the right moment. If a small perturbation shifts a handful of objects across a resonance separatrix, those few may embark on new transport journeys. The effect is hyperlocal and hard to separate from the relentless small pushes already at work. Think of tossing a pebble into a river that's been carving its path for eons. You can make ripples, but the current had plans before you arrived. Comet shower probabilities live in this same statistical neighborhood. A true shower at Earth requires synchronized delivery of many bodies onto Earth, approaching orbits within a limited window. That kind of synchronization rarely comes from inner system trifles. It's more often the signature of slow, coherent drivers, galactic tides or distant stellar nudges, tipping outer reservoirs so that many objects start long, similar journeys sunward. The belts contribute steady weather, punctuated by occasional, minor squalls when a family breakup floods a narrow range of orbits with fragments. Even then, observational reality is humbling. Meteor streams you see lighting up the sky are usually the ashes of comets already committed to short-period lives, not sudden gifts from the far frontier. So how would we hunt for new songs in the belt's background hum? First, by counting obsessively. Survey completeness is the villain of subtlety. You can't detect a 2% change if last decade's catalogue missed 30% of the players. Wide-field surveys that revisit the same sky with clockwork cadence let us build controlled baselines. How many small bodies in which resonances, with what ranges of eccentricity and inclination, repeat the census with the same biases and the same detection pipeline, and differences begin to mean something. Boring methodology is a superpower. Second, by tagging families and following their fates. Collisional families start tight in orbital element space. Over time, thermal drift and resonant puffs smear them. If a boundary moved or a leak opened, the smearing pattern records it. The family becomes a die in the dynamical flow, tracing eddies you can't otherwise see. It's planetary forensics with patience and spreadsheets. Third, by watching the feedstock at the halfway houses, centaurs are the short-lived brokers between Kuiper Belt and inner-world comets. Track their inclinations, perihelia, and lifetimes, and you monitor the valves on the long pipeline. A small uptick in centaurs grazing particular mean motion commensurabilities can be the first whisper of a future rise in short-period comets years down the line. Sprinkle in dynamical clones in simulations, and you turn that whisper into a forecast cone. Not which comet when, but how many and of what flavor. Finally, we listen in wavelengths you wouldn't expect. Dust betrays motion. In the inner system, resonant rings in the zodiacal cloud wax and wane as grains are trapped or lost. In the outer system, a faint change in the surface brightness profile of cold dust bands could hint at recent stirring, even if the parent bodies remain below detection limits. When rocks won't speak up, their crumbs gossip. If you came for symbols, the belts will disappoint. If you brought a stethoscope, they won't shut up. The wind chimes keep playing, and with enough time and data, you can hear when the breeze veers by a degree. Next, we'll switch from statistics to signatures you can measure in real time, the instruments and methods that would catch any tiny barycentric sneeze or trajectory shuffle. How we'd actually know if the solar system had been nudged. If the solar system sneezes, our instruments say Gesundheit down to microns. That's not bravado. It's the result of half a century spent turning the entire solar system into a metrology laboratory. Did anything move? Is a deceptively hard question in a universe where everything is always in motion. But we've built overlapping yardsticks on planets, around planets, and far beyond them that light up if the barycentered jitters even a hair more than expected. Start with astrometry, the art of measuring where things are on the sky, to ludicrous precision. In the old days, we were thrilled to nail positions to arcseconds. In the Gaia era, we're talking micro-arcseconds, angles so small you could resolve a coin on the moon from Earth. Gaia repeatedly scans the sky and fits positions, parallaxes, and proper motions for billions of stars. Here's the trick. To make sense of those motions, you must model the observer's own dance perfectly. If the solar system's barycenter deviated from its predicted track, even a tiny transient kink, that error would leak into the residuals of countless stellar measurements. You wouldn't see one star jump, you'd see a correlated twitch across the sky that only disappears when you tweak the barycentric ephemeris. Astrometry is therefore a two-way mirror. It tells you where the stars are, and by forcing a consistent solution, it quietly confirms where we are. Zoom from where to when with pulsar timing arrays, PTAs. Millisecond pulsars are nature's atomic clocks, tossing radio ticks with astonishing regularity. Spread a dozen or more across the sky, time their pulses for years, and you build a galactic scale interferometer. A wobble of the solar system barycenter adds a common timing offset, a coherent, direction-dependent pattern in the arrival times that refuses to average away. PTAs were built to chase low-frequency gravitational waves, but the same sensitivity doubles as a barycentric lie detector. If a visitor's gravitational pull nudged the entire solar system ever so slightly for a few weeks, the residuals would show a faint, predictable swoop, small, symmetric, and shared across pulsars in a way you can't fake with local noise. It's the cosmic version of noticing your whole house creaked in unison. Closer to home, spacecraft ranging gives you rulers with timestamps. The Deep Space Network pings probes all over the solar system with radio waves, then measures two-way light time and Doppler shifts with exquisite stability. Cassini, Messenger, Mars orbiters, New Horizons, each returned years of range and velocity data referenced to atomic clocks. Stitch those tracks together, and you get a tight weave binding planets and spacecraft to the barycentric frame. A nudge to the family center shows up as correlated deviations across many, unrelated flight paths. One spacecraft can be cranky. A fleet can't all be cranky, in the same way, unless the reference is to blame. We also measure the Earth-Moon system with almost absurd delicacy. Laser pulses from Earth bounce off retroreflectors left on the Moon, and we time the round trip to millimeters. Lunar laser ranging is mostly famous for testing relativity and tracking the Moon's slow tidal drift, but it also anchors Earth's position in the barycentric frame. If the solar system experienced a brief external tug, Earth's orbit solution would absorb part of the shift. The laser record would keep us honest by refusing to follow any ephemeris that didn't respect the photons. Add sentinels parked at Lagrange points, SOHO and D-SCOA at L1, JWST at L2, plus a parade of solar and Earth watchers. Their orbits are delicate loops in a rotating frame, stabilized by tiny station-keeping burns that are themselves precision measurements of the local gravitational landscape. Because L1 and L2 are sensitive perches, small mismodeling of the Sun-Earth dynamics shows up as increased propellant use or unexpected trim schedules. When navigation teams say the fuel budget matches the book, they're quietly certifying that nothing big snuck into the equations. Inside some spacecraft lurk accelerometers and ultra-stable oscillators that make even subtler checks possible. Drag-free control, tested spectacularly by LISA Pathfinder, can subtract non-gravitational forces until all that remains is pure gravity. The resulting trajectory becomes a joyride for relativists and ephemeris makers. Mix in next-generation deep space atomic clocks, and you can time your way through space-time with fewer assumptions. The more independent ways you can ask, "Did we move?" the less likely you'll be fooled by any one instrument's quirks. How would detection actually look in practice? First, someone notices residuals that won't behave. A PTA team sees a low-level, weeks-long common mode pattern. DSN analysts flag correlated Doppler drifts across multiple probes. Astrometry pipelines report a sky-wide microarcsecond ripple you can't absorb with catalog tweaks. None of these alone is courtroom proof, but together they form a triangulation. You propose a tiny, time-limited perturbation to the barycenter, linked to a specific direction and epoch. Refit everything, pulsar times, spacecraft ranges, Gaia solutions under that hypothesis. If the residuals fall like dominoes, you've caught a sneeze. If they don't, it was instrument weather masquerading as celestial gossip. There's a difference, too, between intrinsic motion and modeled motion. The solar system ephemerides, those dense tables that tell us where every major body is, are global fits to decades of data. Planetary radar, optical tracking, spacecraft ranges, lunar lasers, and more. We don't assume an answer and check it. We infer the answer by forcing consistency across everything. That process is flexible enough to accommodate tiny, real perturbations without drama. In other words, if a 3I-class visitor genuinely left any measurable fingerprint, it would be absorbed into the next generation ephemeris as a minuscule, time-localized correction you'd need a magnifying glass to find. And if you're worried that all of this still misses something, nature kindly adds redundancy. Independent teams build independent ephemeris with different software and priors. Amateur and professional observatories feed astrometry from opposite hemispheres. Radio, optical, and laser techniques span wavelengths and systematics. The overlap isn't wasteful. It's a firewall. Gravity may be simple, but measurement is an art that benefits from multiple brushes. So yes, if the solar system sneezes, we hear it. By how stars appear to wander, how pulsars tick, how spacecraft hum, how the moon listens to our laser knocks, and how quiet orbital perches keep their balance. Detection wouldn't be a headline-friendly spike. It would be a chorus of tiny agreements across very different instruments, all pointing to the same microscopic nudge. Next, we'll indulge the doomsday imagination responsibly. Assemble the most extreme yet physically plausible scenarios for a passerby, and show why the outcome still looks more like a paperwork update than a dinosaur-ending plot twist. Hollywood wants continent surfing. Physics offers slightly rearranged pebbles. If you take the dials we've met so far and turn them to maximum mischief, what do you actually get when a fast interstellar visitor threads our planetary maze? Not the fireworks reel, more like a bureaucratic memo. Please note minor adjustments to a few small bodies, no action required. Start with the loudest plausible event, a grazing encounter with a giant planet. Picture a kilometer-scale interstellar comet barreling past Jupiter, just a few planetary radii above the cloud tops. That's rare, but not absurd. The gravity field there is steep. A near miss can torque the traveler's path, shear off pieces, and flood the local environment with debris. It sounds dramatic until you compare masses. Jupiter is the skyscraper. The comet is a paint chip hitting a windy ledge. The immediate outcomes live in the local and temporary bucket, a bright, short-lived dust envelope. small fragments scattered onto wildly different heliocentric orbits, maybe one or two shards on awkward loops that hang around for a few seasons before being flung away. Jupiter's own state barely blinks. The inner planets, they get a schedule alert that the night sky will be prettier for a bit. And that's about it. Could such a pass seed short-term traffic toward the Sun? Yes, in a limited way. A fragment or two might receive just the right change in direction to lower perihelion, becoming a brighter comet at its next return. But the returns arrive on the visitor's clock, not ours, and hyperbolic guests don't have returns. Even bound fragments, if any, would be small and few, so you trade one dramatic flyby for the possibility of a couple of modest comets years later. That's not a plot twist, it's a programming note. Now, with 12% more sky glow, shift the stage to Saturn or Neptune, and the theme stays the same. The rings of fragile jewelry that don't enjoy close company, but a flyby's debris would mostly sweep through as brief meteor activity, glitter, not gravel. Neptune's distant court is more interesting dynamically. A fragment tossed onto a centaur-like path could wander between the giants for a while, nudged by distant passes until it exits or sunward drifts into a short-period comet. That's a long, meandering story, measured in many orbits, with outcomes that look like statistical weather, not a storm. What about resonant kicks, nudging a few outer small bodies so their long-term evolution changes lane? That's the most credible system echo. Suppose a fragment from the encounter ambles through the Kuiper belt near the blurred border of a resonance. A tiny push at the right phase can slide a resident across the separatrix, setting it on a different, slow diffusion path. Multiply by a handful of opportunities, and you've changed the futures of dozens. Maybe a few hundred if luck overperforms. That's enough to nudge population statistics, so that, decades to centuries out, surveys notice a percent-level drift in how many objects occupy a given dynamical class. If you're hoping for a comet shower at Earth next June, this is not your mechanism. If you're building models of source regions, you might sharpen a bar on a histogram. There's an edgier scenario: tidal shredding of the visitor during a deep pass. A loosely bound nucleus can be pulled into a string of fragments. Some pieces might be temporarily corralled on odd orbits around the giant, others sprayed onto heliocentric arcs with a wide spread in energies. A few could intersect resonance webs more efficiently than the intact parent ever would have, raising the odds of later appearances in the inner solar system. But again, the plural of odds isn't catastrophe. You're still living in a world where most fragments either leave promptly or fade into the small body background, indistinguishable from homegrown comet debris after a handful of orbits. Could the worst-case parade include an actual planetary impact? On paper, yes. Low probability isn't zero, but the geometry is unforgiving. Planets are tiny targets in a huge arena, and fast interstellar approach speeds shrink the window further. A bullseye requires a conspiracy of timing, angle, and intervening tugs that cooperate rather than cancel. If fate insists, the impactor is still small on planetary terms, and while a strike could be locally serious for that world, it's not a solar system rearranging event. The dinosaurs didn't consult hyperbolic dirt. They met a long-period, bound object delivered by the system's own pipelines. You might also ask whether the giant planets could amplify the disturbance, turning a small nudge into a chain reaction. In real dynamics, amplification is picky. It needs resonance matching, repeated coherent kicks, or close encounters that build on each other rather than randomize. A single flyby with fragments doesn't bring that persistence. The default outcome is decorrelation. A few bodies get new phases, then the clockwork of secular precession and distant passes stirs those phases until the memory dissolves into noise. From the perspective of our detectors, the aftermath is equally tame. Spacecraft tracking wouldn't show a family-wide recoil. You'd see individual, tiny course changes when and if any new comets wandered through the inner system. Pulsar timing arrays would yawn. There's no lasting barycentric shove to encode. Astrometry would absorb the whole episode inside routine ephemeris fits without breaking a sweat. The solar system's instruments are ready for drama. The cosmos mostly sends homework. Even the scary-sounding temporary capture around a giant comes with a safety clause. Short-lived loops usually unwind after a few turns unless energy is bled away, which is hard to do without atmospheres, tides, or a helpful companion to carry off the excess. You can imagine a fringe case where a fragment becomes a new irregular moonlet. Congratulations, you've added one pebble to a swarm that already numbers in the dozens. The architecture didn't flinch, so push the envelope as far as physics allows, and the storyline remains stubbornly grounded. A grazing giant planet encounter, some tidally peeled confetti, a few objects nudged onto different long walks, the faintest statistical fingerprint that only archivists with patient databases will love. And that's the spicy version. Planet-moving catastrophes require bodies with real mass, coherent forcing, and time. Our interstellar party guests bring speed and sparkle, not leverage. Next, we'll pivot from why nothing dramatic happens to what smart species do anyway. Catalogue the visitors, sharpen early warning, and practice the gentle arts of trajectory nudging so the boring outcome stays boring on purpose. Planetary defense is space floss, boring until you really need it. The good news is that needing it for something like 3IATLAS is vanishingly unlikely. The better news is that the same habits that protect us from homegrown hazards also make us smarter, faster, and calmer when interstellar surprises show up. Think of this chapter as a checklist taped to civilization's fridge. Find it early, characterize it quickly, decide sanely, and if it's truly big, have tools that nudge, don't panic. Start with the most valuable commodity in space, time. Early warning buys options. That means wider, deeper, and smarter sky coverage so we catch faint movers far from the sun, not dramatic headlines days from perihelion. The to-do here is threefold. First, sustain and expand all sky optical surveys with high cadence so weird motion pops out algorithmically rather than by human squint. Second, add thermal eyes, space-based infrared telescopes that see dark objects glowing with their own heat. They don't care if an object is charcoal black. Third, close the southern and northern coverage gaps and stitch data in near real time. The killer app isn't one big telescope. It's a federated catalog where detections cross-check within minutes, not weeks. The headline writes itself: a snowball from another star system drifts into town, and the first thing we do is point every telescope at it, like paparazzi at a red carpet. That visitor is 3IATLAS, the third confirmed interstellar object to cruise through our celestial neighborhood after 1I Oumuamua and 2I Borisov. 3I is the license plate number astronomers give to interstellar guests in order of discovery. Atlas is the survey that first spotted it. One-liner: interstellar objects are cosmic couch surfers. No address, great stories. Here's the discovery scene. On July 1st, 2025, the Atlas telescope in Rio Hurtado, Chile, flagged a faint, moving dot that didn't fit the usual local patterns. Follow-up checks and orbit fitting showed a trajectory that wasn't closed like a planet's or comet's elliptical path. It was hyperbolic, an open curve that screams, "I'm just passing through." In less than a day, the interstellar nature was confirmed, making this the rarest kind of headline in planetary science. Only the third time in history we've watched material from another star wander into our yard. Names matter here. The I flag means interstellar, separating 3IATLAS from the alphabet soup of ordinary comets and asteroids that were born with the sun. Think of designations as cosmic passport stamps. Oumuamua taught us you can be interstellar and weirdly inert. Borisov showed you can be interstellar and gloriously comety, with a gassy coma and tail. Early images placed 3IAT as squarely in the Borisov camp, fuzzy halo, definite activity, an ice and dust body shedding material as sunlight warms its surface. It's not a rock pretending to be mysterious. It's a comet doing comet things on an interstellar visa. Speed is the giveaway and the thrill. Local comets can get frisky, but 3IATLAS barrels in with tens of kilometers per second of hyperbolic excess speed, velocity. It still has, even after the sun's gravity has had its say. By late 2025, it was clocked at roughly 61 kilometers else, about 37 miles per second, coming from the direction of Sagittarius, not bound to the sun before or after its visit. Translation: no amount of please stay will make it permanent. It was born under a different sky, and it's headed back to one. What about its route? The orbit solution points to a perihelion, closest approach to the sun, in late October 2025, inside the orbit of Mars, followed weeks later by its safest distance pass relative to Earth. Hundreds of millions of kilometers between us, comfortably more than no need to panic territory. If interstellar objects are cosmic door-to-door salespeople, 3IATLAS is the one that never gets within the picket fence. You could wave from the porch. You won't need to hide behind it. Okay, you might ask, how is an interstellar comet actually different from the homegrown variety? Origins and orbits, for starters. Comets and asteroids born here formed in the protoplanetary disk around our young sun, inheriting orbits that are, mostly, ellipses bound to the solar system's center of mass. Interstellar objects, by contrast, were ejected from other systems, likely during planet-building brawls when young giants flung leftover icy rubble into deep space. After untold millions or billions of years drifting between stars, a few wander near us on hyperbolic flybys. If solar system comets are long-distance cousins, interstellar comets are strangers who still somehow bring a dish to dinner. Composition and behavior add more contrast. Even before detailed spectra, the presence of a coma tells us 3IATLAS carries volatile ices that vaporize under sunlight. Early Space Telescope looks in mid-2025, hinted at an unusually CO2-rich coma with water and other volatiles mixed in. A chemical accent that may preserve the climate of the star system where it formed. The coma's brightness also muddies size estimates. Dust glows and makes the nucleus look bigger than it is. Pro tip from comet science: if it's fuzzy, it's busy. Discovery context matters because it shows how our sky police work. Atlas is part of a global early warning network, scanning for fast movers, mostly to spot anything on a dangerous Earth-crossing track. That the same net caught a harmless interstellar wanderer is both luck and design. Wide-field, high-cadence surveys don't care if a thing is famous, they care that it moves weirdly. Once flagged, the baton passes to bigger, sharper instruments, Gemini, Hubble, Webb, that can dissect light into chemistry and watch the coma evolve. In practical terms, it's a relay race where the finish line is we understand where it came from and what it's made of. There's also the psychological jolt. An interstellar object isn't just a postcard from abroad. It's a sample return mission we didn't have to launch. Its atoms crystallized around another star, under different radiation fields and dust recipes. If it were a cookbook, the ingredient list might read like ours, but with surprising proportions. And yes, the jokes write themselves. Photosynthesis is plants bragging about inventing solar panels first. Interstellar comets are the lab exchange students who show up with a cooler full of unknown reagents and say, let's run a spectrum. We oblige. Finally, a quick calibration on expectations. Popular headlines love to inflate a visitor's importance, rogue comet to change everything. But orbital mechanics is a tough bouncer. 3IATLAS offers a scientific feast without drama. No threat to Earth, no sudden sky brightening guaranteed, no cosmic pinball that rearranges planets. It's rare, beautiful, and informative precisely because it refuses to be sensational. The miracle is not catastrophe, it's access. Gravity is the group chat you can't leave. Mass adds you automatically. The invite went out at the birth of the universe, and everything with mass has been replying, seen, ever since. To keep this tidy, let's separate the two big moderators of the chat, Newton and Einstein. Then use their rules to explain how orbits form, why energy and angular momentum are the real currency of motion, and how tiny nudges can cascade into noticeable changes without breaking any cosmic laws. Start with Newton, the pragmatic engineer of the cosmos. His picture of gravity is a force that pulls any two masses together with a strength that scales with their masses and fades with the square of their separation. It's a clean, predictive recipe. Tell me where two bodies are and how fast they move, and I'll tell you where they'll be later. Crucially, in Newton's world, an orbit is just a perpetual fall that misses. A planet keeps aiming for the sun, but overshoots because it's moving sideways fast enough. The result is an ellipse, circle, parabola, or hyperbola. The shape depends on energy. A negative total mechanical energy, kinetic plus gravitational potential, binds you to an ellipse. Exactly zero tips you onto a parabolic escape. Positive energy launches you on a hyperbola. Like relationship statuses, the sign tells you whether you're staying, it's complicated, or leaving forever. Einstein didn't cancel Newton. He explained why Newton's recipe works so well and where it needs seasoning. In general relativity, mass and energy tell space-time how to curve, and curved space-time tells matter how to move. Orbits aren't paths forced by a distance-acting pull, they're geodesics, the straightest possible lines in a warped geometry. Around the sun, space-time is shaped like a gently sloped funnel with a deep, narrow dimple at the center. Objects move along the landscape, close passes slide deeper, and whip around faster. For most solar system business, Newton's shortcut nails it. Einstein becomes essential when speeds approach light, gravity gets intense, or you need exquisite precision. Think Mercury's perihelion precession, or GPS clocks keeping time correctly. If Newton is a great map, Einstein is the globe that explains why the map's edges don't quite fit. Now to the heart of orbital behavior, energy and angular momentum. Picture energy as your budget and angular momentum as your receipt that proves how you spent it. You can trade kinetic for potential energy by climbing away from a gravitating body, slowing down as you go, or trade potential for kinetic by diving inward, speeding up. But unless a separate force transfers energy in or out, your total stays fixed. Angular momentum is even fussier. In a central force field like gravity, it's conserved unless something torques you. That conservation compacts into Kepler's second law. Equal areas swept in equal times. When you're near periapsis, closest approach, you move fast. Near apoapsis, furthest point, you loaf. The product of speed and the distance at right angles to your path stays constant, like a skater pulling in their arms to spin faster. This bookkeeping explains orbit shapes without invoking mysticism. Give a body just the right sideways push at a given distance, and you set its ellipse. Change that push and you warp the ellipse's size or tilt. Push too hard and you flip the ledger to positive energy. Goodbye, you're on a one-way hyperbola. Push not quite enough and you graze the parabolic tipping point, asymptotically escaping with barely a coin left in the kinetic wallet. It also clarifies why falling in speeds you up. You're converting potential energy into motion while preserving angular momentum, so the tighter radius demands a higher speed. What about the births of orbits? Nature's favorite method is messy. Clouds of gas collapse under self-gravity, and random motions average into a preferred spin. Conservation of angular momentum squeezes the chaos into a flattened disk because motion perpendicular to the spin cancels more easily than motion in the plane. Dust sticks to dust, pebbles snowball into planetesimals, and over time you get worlds coasting along the disk's plane. Their orbits emerge as a compromise among initial velocities, collisions, and gentle interactions with the gas. A celestial version of musical chairs that ends when the gas disperses and the remaining bodies settle into long-lived tracks. Even in a tidy two-body dance, small nudges matter. Add a tiny impulse, say a puff of gas from a comet jet or a micrometeor strike, and you change either the energy, speed, or the angular momentum direction, sometimes both. Because the orbital equations are non-linear, the response isn't always proportional. A minuscule change at the right point in the orbit, near periapsis, where speeds are high, can noticeably rotate the ellipse or shift its size. Engineers exploit this ruthlessly. In space navigation, periapsis kicks deliver the most bang per unit of fuel, like pushing someone on a swing at just the right moment. The same math underlies gravity assists. You borrow a sliver of a planet's orbital momentum to reshape your trajectory, paying it back by imperceptibly altering the planet's motion. The planet is so massive, the price is a rounding error. For a spacecraft, it's a jackpot. One subtlety worth savoring: energy and angular momentum conservation are local truths that survive complicated environments, but how they're partitioned can drift through a series of tiny exchanges. Picture a coin jar that never changes total number of coins, but pennies keep becoming nickels and back again. Over many orbits, repeated microscopic tugs, sunlight pressure, thermal re-emission, the Yarkovsky effect for small bodies, or feathery outgassing can ratchet a path inward or outward by small amounts. It's patient engineering by physics. No drama, just accumulation. So where do Newton and Einstein meet your intuition? Newton hands you the calculator and says, "For most problems, I've got you." Einstein leans in to remind you the calculator sits on a curved table. Between them, the rules are consistent. Orbits are sustained, falls shaped by budgets, energy and receipts, angular momentum, and little nudges, well-timed, can rewrite itineraries without breaking the bank. Next up, we'll zoom out from single objects to the whole family photo. How the solar system keeps its overall balance, who subtly leads the waltz, and why the center of that dance isn't exactly at the sun's center. Our planets are in a decades-long slow dance. Jupiter leads, Earth tries not to step on toes. If you want to understand why that dance doesn't end in a pile-up of worlds, you need the accountant's view of gravity. Who holds the mass, where the center of mass actually sits, how rhythm's resonances keep time, and why the whole arrangement is robust with a few squeaky floorboards. Start with the ledger's first line, the center of mass or barycenter. It's the point where the weighted positions of all bodies add up to zero. Think of it as the balance point of the entire system. Because the sun contains the lion's share of mass, the barycenter usually lies inside it, but not at its geometric center. Jupiter, with its colossal bulk, yanks hard enough that the sun actually orbits this barycenter, tracing a tiny loop roughly every 12 years. From a god's eye view, neither the sun nor Jupiter sits still. Both whirl around that invisible balance point like dance partners locked arm in arm. The same is true for every pair and for the system as a whole. Nested loops within loops, all reconciling to one grand balance. Jupiter's influence is headline material, but it isn't acting alone. Saturn chips in a respectable tug. Together, the JS duo shifts the barycenter farther from the sun's center than Jupiter could by itself. This subtle choreography matters for precision timing, spacecraft navigation, pulsar timing experiments that reference the solar system's motion, and even for understanding how the sun's slight barycentric wander might correlate with solar activity. Spoiler, correlation claims are contested. The punchline is simple. The sun is not the unmoving anchor. It's the heavyweight who still has to share the seesaw. Zoom in from the center of mass to the metronomes that regulate the dance, orbital resonances. A resonance occurs when two orbital periods form a simple ratio, say 2.1 or 3.2, so that gravitational nudges repeat at the same place in the orbit, stacking like pushes on a swing. Resonances can be stabilizing, confining bodies into tidy configurations, or destabilizing, clearing gaps like a bouncer with a strict guest list. The poster children for stabilizing resonance are the Galilean moons Io, Europa, and Ganymede in a 1-2-4 chain, the Laplace resonance. Each time Io laps Europa, their lineup repeats. and the gravitational tugs cycle in a way that locks in long-term timing. Energy doesn't magically appear. It shuffles between orbital eccentricity and tidal heating. On Io, that means volcanoes throwing tantrums on schedule. In the asteroid belt, by contrast, resonances with Jupiter open Kirkwood gaps, regions where asteroids are scarce because repeated tugs pump their eccentricities until they're flung elsewhere. Same physics, different outcomes. Rhythm as either a groove or a grinder. Neptune and Pluto give us a stabilizing twist. They're in a 3-2 mean motion resonance, which ensures that when Pluto crosses Neptune's orbit in projection, their longitudes conspire to keep them far apart in reality. It's orbital aikido. The pattern of encounters reduces close-pass risk rather than amplifying it. Farther out, the Kuiper belt is laced with resonant clans, Plutinos, Tutinos, many of which were shepherded into place when Neptune migrated outward in the early solar system. Migration tuned the orchestra. Resonance kept the beat. Resonances aren't only about period ratios. Secular resonances work on slow angles, longitudes of perihelion and nodes, trading eccentricity and inclination over million-year timescales. These are the quiet accountants of orbital elements, shifting risk around the portfolio. A small body can sit in a region where its perihelion slowly processes in step with the giant planets, and over eons its orbit may stretch or tilt. Nothing dramatic on the nightly news, but give it 10 million years and the before and after photos don't look like the same asteroid. So why is the system stable, usually? Stability here doesn't mean perfect predictability forever. It means bounded, non-catastrophic behavior over vast spans. Several factors help. First, spacing. The major planets sit multiple mutual Hill radii apart, where a Hill radius is the zone of a planet's local gravitational dominance. Being separated by multiple Hill radii is the celestial version of personal space. It minimizes disruptive close encounters. Second, angular momentum partitioning. The outer giants hoard most of it, acting as flywheels that resist rapid changes. Third, damping history. Early collisions, gas drag, and migration pruned the wilder configurations, leaving survivors in relatively quiescent lanes. Yet the word usually earns its keep. The solar system is weakly chaotic in the mathematical sense. Tiny differences in today's positions can grow into noticeable phase shifts over tens of millions of years. Mercury, being small, close to the Sun, and influenced by relativistic precession, sits near the edge of some secular resonances. There are low probability pathways where its eccentricity could be excited significantly on giga-year timescales. That doesn't spell doom. It simply says the forecast has error bars that widen with time. Chaos here is not a demolition plan. It's a gentle fog. Stability is also dynamic. The asteroid belt's emptiness is an artifact of past instability. Resonance-driven clearing. The Trojans, asteroids corralled around Jupiter's L4 and L5 Lagrange points, are examples of stable niches carved by the same gravity that emptied others. Lagrange points themselves are like balance beams in the rotating frame, some stable, some not. Park a small body in a stable one, and it can linger for eons. Drop it on an unstable one, and it slides away with the patience of a marble on a shallow slope. This balance sheet perspective pays dividends when you contemplate perturbations. Because so much angular momentum is sequestered in the giants, and because resonant structures act like locks in a canal, small external tugs are usually absorbed, deflected, or dispersed without rewriting the whole choreography. The music might modulate a key, the band doesn't break up. If you wanted systemic chaos, you'd need sustained or resonant forcing at just the right frequencies, or a bruisingly close encounter with something hefty. In short, the solar system remains upright because mass distribution, spacing, and rhythms conspire in our favor. Jupiter conducts, Saturn harmonizes, the inner planets keep tempo, and countless smaller bodies rattle percussion in the background. We live in a symphony that tolerates the occasional wrong note, without throwing the instruments at the audience. Next up, we'll ask how an interloper tries to elbow into this ballroom, the mechanics of a close flyby, why gravitational assists work, and what it would take for a passerby to deliver an actual shove rather than a polite nudge. A gravity assist is cosmic judo. Use their mass to flip your path. Picture a fast traveler skimming past a planet. Up close, the trajectory bends like a stone curling around a whirlpool. Far away, that small bend blossoms into a brand new course around the sun. The planet hardly notices when you bump a freight train. The freight train does not file a complaint, but the traveler can gain or shed astonishing speed relative to the sun with no fuel spent and no rules broken. The secret lives in which movie you watch. In the planet's own movie, the passerby rushes in, swings around on a tidy hyperbola, and departs with the same speed it had when it arrived, only the direction changes. Switch to the sun's movie, and the plot twist appears. Because the planet itself is sprinting around the sun, the bend happens on a moving stage. If the traveler exits in roughly the planet's running direction, it leaves the sun going faster. Peel off the other way, and it leaves slower. Energy hasn't been conjured from nowhere. The planet quietly pays the bill by surrendering or stealing a microscopic slice of its orbital energy. For a spacecraft, that slice is a banquet. For a giant planet, it's a lost breadcrumb. Close encounter mechanics are all about the depth and aim of the swing. The deeper the skim, down to safe limits, the larger the turn, the better you align the exit with the planet's motion, the bigger the payoff. Navigators plan this in a target plane, perpendicular to the incoming path, where a nudge of only millimeters per second, weeks in advance, can move the impact point by hundreds of kilometers and completely rewrite the downstream route. It's like adjusting a bowling ball by a hair at the release and watching the pins explode in a totally different pattern. Space is sensitive. It takes hints very seriously. If you want intuition without a thicket of algebra, lean on the impulse approximation. Treat the whole tug as a swift kick delivered near closest approach. The direction of that kick depends on how you arrive. The size depends on how near you dare to slide past. This picture is crude but useful. It explains why periapsis timing matters. Pushing the swing at the bottom beats pushing at the top, and why fast interstellar visitors are tricky to deflect. When something charges in already screaming fast, the planet barely has time to curve it. The kick becomes a tap, great for a tidy postcard, not great for a dramatic reroute. There's a spectrum of outcomes. A soft flyby with a wide miss gently edits the path and spreads risk thinly. A deep graze near a planet's atmosphere, rings, or radiation belts buys more turning, at the cost of hazards nobody wants: heating, drag, sputtering, stray boulder fields, electronics toasting particles. Nature doesn't sign waivers, so natural bodies sample the full menu by chance. Engineers don't. They eat what the safety office approves. When does a passerby transfer momentum to the sun-planet system in a way that matters beyond one traveler's itinerary? Always, in principle, every assist trades a sliver of momentum between participants, but almost never in a way that the system notices. The total momentum of the sun plus all planets is conserved unless an outsider participates in the exchange. A flyby simply shuffles momentum internally. The traveler leaves richer or poorer. The planet leaves poorer or richer by a barely measurable whisper. To noticeably alter the family's shared state, the outsider must be hefty and slow enough, and the geometry must be unkind enough that the planet's whisper becomes a mutter. That's rare. Think bowling ball into a school bus. Technically, an interaction, practically a shrug. Another path to really change things is capture, but gravity alone is stingy. To bind a fast visitor to a planet or to the sun, you need to bleed away energy through atmospheric drag, tidal heating, or a three-body handoff where a companion gets ejected, carrying excess energy. Those are special conditions, not the default. Most travelers remain what their hyperbolas advertise, just visiting. Flybys can be chained like clever dominoes. By staging encounters, One inner planet to re-aim, another to boost, a giant to finish. You amplify modest turns into long-haul transformations. The choreography must respect windows. Planets move, launch dates drift, and small targeting errors compound. Yet the reward is remarkable reach. You go where your fuel alone could never buy you, because you spend orbital mechanics instead of propellant. It's the ultimate points program. Collect miles from planets that never read the terms and conditions. All of this also explains why the timing and place of a nudge matter so much. A tiny corrective burn, delivered days before a flyby, can change the entry angle into the planet's gravity well, which changes the outbound aim, which sets which opportunities even exist next. By the time you're at closest approach, the geometry is mostly destiny. Earlier is cheaper, later is louder, but less effective. Space navigation has the same rule as procrastination: pay a little now or a lot later. As for interstellar interlopers, their calling card is large approach speed that trims the turning angle and limits how much a single planetary pass can shape their fate. They can still lean on a giant for a tweak, but the word is tweak. To make the leap from postcard guest to household shaker, an outsider would need mass in the planetary class and a slow, well-aimed approach, more rogue world than stray snowball. The universe allows that, but it doesn't pass by every decade asking to move furniture. So a flyby becomes a shove when geometry, timing, and the planet's own sprint align. And the shove almost always matters far more to the passerby than to the planet. Rotate in the local frame, cash out in the sun's frame, and let conservation laws balance the books while you surf a river of moving gravity. Even the sun does a tiny shimmy. Think disco ball, not bulldozer. From far away, it looks like the fixed anchor of everything. But zoom in on the bookkeeping and you discover a star that never sits exactly at its own center. It wobbles in response to whoever is tugging hardest at the moment, tracing loops and squiggles that, stitched together, look like a spirograph drawn by a patient giant. This reflex motion is not decoration. It's the receipt that gravity prints whenever masses share a system. Start with the idea that the center of the solar system is a moving target, the barycenter. It's the balance point where the weighted positions of all bodies cancel out. The sun endlessly circles that point, sometimes deep within its own interior, sometimes a hair outside its surface, depending on the current lineup of heavy hitters. The path isn't a neat circle, it's a changing rosette whose size and orientation drift as planetary phases beat against one another. If you plotted the sun's position day by day in a frame tied to the barycenter, you'd see a tangled but lawful scribble, like a dancer following cues from an orchestra with many tempo lines. This wobble isn't just geometric trivia, it leaves fingerprints everywhere. Precision matters. One fingerprint is kinematic, the sun's center of light, what we'd infer from Doppler shifts, and its center of mass aren't always at the same place doing the same thing, because surface flows, magnetism, and rotation add their own small signatures. Another fingerprint is dynamical. Spacecraft navigation and planetary ephemerides quietly rely on an accurate barycentric frame. When mission controllers say a probe is here, what they mean is here relative to the system's balance point. And that here only makes sense after we've subtracted the sun's shimmy. Helioseismology, the study of ripples running through the sun, adds a third fingerprint. Acoustic waves skim around inside the star, their patterns sensitive to both internal structure and bulk motion. Tiny velocity fields tied to the wobble can, over long integrations, imprint timing offsets in those waves. Think of it as listening to a bell that's ringing, while the bell's mount drifts by millimeters. The tone stays true, but the Doppler pennies clink now and then in the data jar. Because wobble is gravity's signature, it also becomes a tool to detect worlds around other stars. The classic radial velocity technique watches a star's spectrum for a periodic blue-red sway as it circles its own barycenter with planets unseen. Our sun would present such a signal to a distant eavesdropper, a slow, multi-note chord rather than a single tone, because many planets contribute. The reflex curves for massive, far-out companions are long and broad. Small, close-in companions add faster, shallower wiggles. Read correctly. The wobble is not noise, it's a confession. So what would a passerby do to this picture? Imagine a visiting mass sauntering through the neighborhood. For the brief window, when it shares space with us, the barycenter temporarily shifts to include the guest. The sun's path acquires an extra kink, a short-lived detour proportional to the interloper's mass and the geometry of the flyby. Most visitors are lightweights. Their signature is a tremor against the ongoing dance. When the guest leaves, the barycenter returns to its familiar family average, and the sun resumes its ordinary loops as if nothing happened, because for most guests, nothing structurally did. Could a passing object tweak the solar system's overall motion in a way that persists after it's gone? Only if the exchange changes the shared momentum of the system relative to the outside world. Internal trades, sun to planet, planet to planet, can't do that. An outsider represents new books on the shelf during a close passage or collision. Momentum can be traded between insider and outsider, but the scale matters. A small interloper's contribution is a wrinkle you need very careful instruments to notice, and even then, it fades into the dominant budget the moment the visitor departs. The takeaway is mildly disappointing but deeply reassuring. The ledger is vast, and tiny IOUs get lost in the zeros. This leads to the phrase that sounds dramatic but needs decoding: changing the solar system's orbit. Orbit around what? Inside the solar system, every body's path is measured relative to the barycenter, which itself slides because of the family's internal tugs. None of that touches our long-haul route through the Milky Way. On galactic scales, the solar system is a single, bundled mass moving in the galaxy's gravitational field, like a car on a freeway with snacks shuffling in the glove box. When people fret about a comet changing our orbit, they often mean the glove box snacks. The freeway speed and lane are almost entirely set by the galaxy's mass distribution, and by encounters with truly heavyweight outsiders, passing stars, giant molecular clouds, or on truly grand timescales, the tides from the galaxy's disk and halo. Those are the bulldozers. Visitors the size of mountains are glitter in the air conditioning. There is, however, a subtlety worth savoring. Even if a visitor fails to impart lasting motion to the family caravan, its temporary presence can slightly redirect internal trajectories in ways that persist. The sun's added kink fades, but a minor asteroid's orbital phase might be nudged. A dust stream might get detoured. A comet's jet might fire at a different solar distance next time. The wobble and the whisper interact, and while the wobble forgets, the whisper may leave a note for future orbits to find. It's the difference between pushing a swing and briefly pressing your finger into wet clay. Taken together, the sun's shimmy is a daily reminder that center is a role, not a location. The role is set by a negotiation among all masses present, and the negotiation updates constantly. A passerby can sit at the table, but unless it brings serious voting power, the minutes read the same as last week. That's not boring, it's elegant. Stability emerges not from stillness, but from choreography. Next, we'll widen the lens from the family room to the neighborhood. The path our whole system traces around the galaxy. The vertical bob through the galactic disk, and why any nudge from a small visitor gets drowned out by headwinds on that much bigger road. We're already doing 220 kilometers around the galaxy. No, we don't get frequent flyer miles. The solar system isn't parked. It's a passenger rail car hooked to a very long, very fast train called the Milky Way disk. Picture a smooth, sweeping orbit around the galactic center with some jazz improvisation, a gentle inward-outward sway, a bobbing motion above and below the disk, and occasional scenery changes as we drift past spiral structure. Against this backdrop, a visitor like 3IATLAS is a fruit fly catching a ride, real measurable up close and cosmically irrelevant to where the train is going. Start with the big loop. Our orbit around the Milky Way's center is set by the galaxy's mass, the bulge at the core, the starry disk, and the dark matter halo that does the heavy lifting. The speed, call it roughly 200 kilometers per second, is the balance between falling inward and missing sideways, a scaled-up version of what keeps Earth bound to the Sun. One lap takes on the order of a couple of 100 million years, the infamous galactic year. Humans didn't evolve the last time we were here. Dinosaurs were debating feathers. If orbits had loyalty programs, we'd be platinum just from persistence. The motion isn't a perfect circle. It's a nearly circular track with epicyclic flare, small oscillations in and out, as we surf the galaxy's gravitational gradients. Think of it as a runner veering slightly toward and away from the center while staying on the lane. Add to that a vertical bounce through the thin disk. We cross the midplane, rise a few dozen parsecs, fall back, and repeat over tens of millions of years. It's a spring on a rail vibe, set by the disk's restoring gravity. The exact amplitudes and periods depend on how much mass is packed locally and how fast we're gliding along. But the feel is consistent, gentle, predictable, and not subject to whimsy, because the galaxy spins differentially. Inner regions lap the outer lanes. The interstellar scenery slides past. Spiral arms aren't fixed, solid bands. They behave more like traffic waves. We periodically find ourselves near an arm's denser gas and star fields, then drift into quieter stretches. None of this requires a kick from a wandering pebble. The pattern is baked into the mass distribution. It's the background music you didn't realize you were dancing to. Now the headwinds. Moving through the interstellar medium sounds like it should be windy, but space is emptier than your fridge during finals week. The drag on a compact, gravitationally tightly bound system like ours is effectively zero. What about magnetic fields threading the disk? They guide charged particles and shape cosmic rays, but they don't grab the solar system and haul it somewhere else. The large-scale net effect on our center of mass is a shrug. Even gravitational dynamical friction, the slow back reaction felt by very massive objects plowing through a sea of lighter ones, demands a mass budget we simply don't have. Star clusters feel it over eons. A star plus planets package cruising the disk does not. Could passing near giant molecular clouds or star clusters matter? These are the real lane shifters, at least in principle. A close approach to something that carries millions of solar masses can torque a stellar orbit a bit. Tweak the radial or vertical oscillation, alter phase, maybe add a small kink to the long record. But close on galactic scales means distances that would park such a cloud uncomfortably bright in our sky. And the timing is measured in once in many tens of millions of years. It's a rare nudge, not an everyday breeze. Enter 3IATLAS, a compact, icy body, likely a kilometer or so across, blasting through the solar system on a hyperbolic pass. In the neighborhood, it's dramatic. High speed, a glowing coma. A great excuse to schedule telescope time at 3 a.m. But could it move our orbit around the Milky Way in any way you'd notice outside a spreadsheet with too many decimals? No. To change the solar system's galactic trajectory, you must change the momentum of the entire bound package relative to the galaxy. Internal shuffling, sun tugs planet, planet tugs comet, comet tugs nothing in particular, doesn't alter the group's shared motion. An outsider can, in principle, add or remove a morsel of momentum, but the scale of 3I's contribution, compared with the Sun's 220 kilometer cruise and 2 octillion kilogram mass, is like whispering at a rock concert. Even if you imagine the most dramatic option, a direct hit on the Sun, your galactic delta V would be unbelievably tiny. The impact would be a great physics demonstration in the photosphere and a rounding error in the solar system's ledger. And because the visitor is gone afterward, there's no continuing external force to push us. The train resumes the same track it always had, minus a number in the 12th decimal place of something only a pulsar timing specialist would care about. A more subtle question is whether 3I could alter the phase of our smaller oscillations, shift exactly where we are in our in-out, or up-down bobbing. That would require a measurable torque on the solar system's mass distribution or a lasting change in the internal arrangement that feeds back on the whole. But the inner machinery is dominated by the sun and giant planets. A tiny transient tug on a dust-to-asteroid scale component doesn't rebound up the hierarchy to move the center of mass motion in any meaningful way. It's the classic butterfly effect caveat turned around. Some butterflies flap in rooms with soundproofing. This is oddly good news for storytelling. You can frame the adventure of interstellar visitors without pretending they wrench the steering wheel. The narrative becomes richer. We're a small caravan tearing around a galactic highway, practicing perfect lane discipline thanks to gravity's rules, while interesting hitchhikers sometimes hop aboard, share their chemistry, and hop off. The thrill is the sampling, not the shove. Besides, 220 kilometers is already a flex. The universe doesn't owe us more drama, it owes us better detectors. Next, we'll zoom in on those background forces that actually can shape populations over time. Galactic tides and local versus global gravitational fields, and use them to sort real movers from tap-on-the-shoulder pretenders. If gravity were a concert, the galaxy is the subwoofer. 3I is someone tapping your shoulder, tides. In this context, aren't waves or sea spray. They're the slow, inexorable stretching that happens because different parts of a system feel slightly different pulls. The Milky Way's mass isn't sitting at one neat point. It's smeared across bulge, disk, and halo. That spread means the sun and the far reaches of our comet reservoirs don't feel exactly the same acceleration. The mismatch is tiny near the planets, stronger on the outskirts, and patient everywhere. Given enough time, patience beats enthusiasm. Start with the playground where galactic tides do their best work. The Oort cloud, that distant spherical pantry of icy leftovers extending tens of thousands of astronomical units from the sun. Out there, the sun's grip is a whisper. The galaxy's tidal field acts like a slow hand on a dimmer switch, gently tilting comet orbits, altering their perihelia, and every so often, sliding one onto a path that drops it sunward. It's not a thrill ride. It's a scheduling algorithm. Some epochs see a trickle of comets. Others, after the right combination of tides and chance, see a modest uptick. The inner solar system barely notices the tide directly. The sun's near field dominates here, but its long arm reaches the cloud's edge where the leash is long and the dog, frankly, distractible. Now compare that steady tug with a plausible shove from 3IATLAS. A kilometer-scale visitor streaking through the inner system is a sprint, fast, localized, and over in a planetary blink. Its gravitational sphere of influence is effectively pocket-sized. Even if it threads a path that brushes a minor asteroid or dust stream, the lasting effect is confined to the tiny neighborhood it actually approaches. Tides, by contrast, don't care where you are today. They care where you are on average for millions of years. A subwoofer makes the whole room hum. A tap on the shoulder fades before you decide whether to turn. If you're hunting for real movers, agents that can alter the statistics of orbits across entire populations, you graduate from lone visitors to heavyweight passers-by. Nearby giant molecular clouds and rogue stars own that title. A star of solar mass wandering within a light year delivers a system-wide nudge to the Oort cloud, re-aiming a not small fraction of comets. A truly close brush by a cloud with 1 million suns worth of mass carries both heft and volume. It doesn't just tug, it shepherds the local gravitational landscape for millions of years as we cruise through its outskirts. You won't see a single dramatic jolt. You'll see a long, low-frequency remix of outer orbits that statistically seeds more sun grazers. The key is coherence. A small body, like 3I, interacts with a vanishingly tiny slice of the solar system at a single time and place. A passing star's reach intersects a huge swath of the Oort cloud simultaneously, pushing many objects in correlated ways. Coherence makes signals grow. Isolated pokes just average away. It's the difference between a stadium chanting in unison and one person coughing in row 27. Spiral arm passages can add spice. Arms are not rigid structures. They're density waves where gas and dust pile up, birthing stars and thickening the gravitational field a little. When the sun's orbit threads one, the local tide strengthens, and the rate at which outer comets are nudged can tick upward. Layer that with the occasional open cluster or association drifting nearby, and you get errors when the outer pantry is rattled more than usual. None of this drama depends on interstellar pebbles wandering through our living room. It's about what's happening to the neighborhood, not who knocked on the door. There's also geometry. Galactic tides have preferred directions, a vertical component that tries to pull things toward the disk's midplane, and a radial component that stretches along the line to the galactic center while squeezing perpendicular to it. That anisotropy imprints itself on comet orbits over time, subtly biasing the directions from which long-period comets arrive. Passing stars and clouds don't completely erase this pattern. They add stochastic kicks on top of the tidal baseline. When you see a distribution of inbound comets with faint preferences in angle and timing, you're reading the room's acoustics, not the footsteps of a single dancer. Timescale seals the case. The 3i spectacle occupies months in our telescopes, and days near perihelion. The tide writes in millions of years, and edits in tens of millions. If you plot influence versus time, 3i spikes early and decays to zero. The tide is a flat line that never quite sleeps. Systems evolve under the integrals, not the spikes. Given aeons, a faint gradient beats any brief gust. None of this should make 3i scientifically boring. Its chemistry is a message in a bottle from some other sun. Its dust and volatiles widen the sample of how worlds assemble beyond our bubble. But if the question is, who rearranges orbits for a living, galactic structure, stellar flybys, and massive clouds collect the paycheck? Small visitors are storytellers, not movers. One practical upshot is how we design surveys. If you want to understand the reshaping of near-Earth space today, you watch resonances and minor body collisions. If you want to grasp long-term supply lines of comets, you model the tide, track nearby stellar trajectories, and map dense clouds along our future path. Forecasting a comet shower is more about galactic geography and stellar census than about spotting the next interstellar tourist. So we give the subwoofer its due and the shoulder tap its charm. Let 3i hand us chemistry. Let the galaxy handle architecture. When we next turn the page, we'll bring chaos into the room. How small, well-placed nudges can grow within multi-body systems, and where the solar system is actually sensitive to a millimeter turning into a mile. Space chaos, where a millimeter today becomes an awkward kilometer tomorrow. In celestial mechanics, chaos doesn't mean fireworks. It means trajectories that diverge exponentially from nearly identical starting points. Two pebbles leave the same gravitational pinball table, with a separation you couldn't slide a virus through. A few million orbits later, one is sunbathing near Mars, and the other is learning humility beyond Neptune. No magic, just sensitive dependence on initial conditions woven through multi-body gravity. The key quantity is the Lyampunov time, how long it takes tiny errors to blow up by a factor of e. For many small body orbits, that timescale is short enough to matter for human planning and long enough to be invisible in the moment. You can compute fancier diagnostics, MIGNO maps, frequency modulation checks, but the intuition is simple. Some regions of phase space are quiet libraries, others are raucous cafes. Whisper in a library and your words persist. Whisper in the cafe and they're swallowed in seconds. Where does the cafe live? Start with resonance overlap. When two or more mean motion resonances lie close enough, their borders smear and a stochastic layer forms. An object wandering into this neighborhood is jostled randomly from one resonant influence to another. This is the Chirikov criterion in action. Once the widths overlap, islands of regular motion dissolve into a sea. In the main asteroid belt, such overlap laces the map between the tidy islands, great for dynamical tourism, terrible for long-term stability. A boulder that drifts slightly in semi-major axis, say from uneven heating or outgassing, can cross from calm water to white water and never find its way back. Sensitivity windows aren't distributed evenly. They cluster where a nudge gets the most leverage. Perihelion passages are prime real estate. At closest approach to the Sun or to a planet during a near pass, velocities are highest, directions swing fastest, and gravitational tugs accumulate meaningfully. A millimeter per second tweak days before perihelion can morph a close but safe planetary pass into a barely miss or a grazing encounter that reroutes the next century. Space navigators exploit this. Nature does too, through jets on comets, micro-collisions, and the occasional shove from a neighbor. Secular dynamics provides a quieter, sneakier path to chaos. Instead of resonances that repeat every few orbits, secular interactions tune the slow precession of orbits, the way perihelia and nodes rotate over long times. When a small body's precession rate matches a background mode set by the giants, its eccentricity or inclination can be pumped in a long, gentle crescendo. Layer a weak mean motion resonance on top, and you get a diffusion machine. The object's eccentricity creeps upward until, eventually, a planetary encounter becomes possible, and then the dice are rolled again. It's the dynamical equivalent of compound interest, boring day to day, lethal over decades. The asteroid belt hosts textbook examples. Between the well-known gaps lie transport corridors, where secular and mean motion effects cooperate to raise eccentricity, just enough that Mars or Earth enters the chat. One small rock's path may be predictable for centuries. A statistical cloud of clones, each beginning with micrometer-scale differences, fans out like smoke, some clones entering Earth crossing space, others draining outward toward Jupiter's influence. The lesson is not that prediction fails. It changes form. You trade deterministic forecasts for probability flux. How likely is an object to be in a given dynamical class at a given time? Slide outward to the Kuiper belt and the scattering disk, where Neptune is the quiet conductor of chaos. Objects with perihelia near Neptune's reach can random walk in semi-major axis via repeated distant encounters, no single pass dramatic. The ensemble transformative. Here the Kozai-Lidov mechanism sometimes joins, trading inclination for eccentricity when an object's argument of perihelion liberates. The orbit tilts up, the perihelion drops, and a distant, cold wanderer becomes a warmer, riskier visitor. Flip the process and you can protect an object by lifting its perihelion out of harm's way, decoupling it from Neptune's grip. Protection and peril use the same math. Context decides which wins. Resonant trans-Neptunian objects offer a second flavor. Inside a stable resonance cell, motion is regular. Graze the separatrix, the thin boundary between libration and circulation, and you can tumble into the chaotic layer. Diffusion from such layers seeds the scattering disk with fresh recruits while also leaking members back into resonance. Over tens of millions of years, populations breathe through these dynamical membranes. If you imagine the Kuiper belt as a coral reef, the separaries are surf zones, rich, noisy, and constantly rearranging who lives where. Even dust feels the dance. Pointing Robertson drag, sunlight stealing a whisper of angular momentum from tiny grains, slides particles inward over long spans. On the way, they encounter resonance webs with planets. Some grains are captured and shepherded, building resonant rings. Others skim chaotic edges and are ejected or ground down in collisions. The structure you see in zodiacal light, or exozodiacal disks, is not a static decoration. It is the time-averaged portrait of countless chaotic microjourneys. The practical upshot is that sensitivity is both a curse and a diagnostic. For space missions, you schedule early, cheap corrections to dodge the cafes. For population science, you embrace ensembles and map transport rates between regions of phase space. You can't say which exact rock will be nudged into a near-Earth orbit in 2 million years, but you can say how many per million years, from which corridors, and with what orbital flavors. In this sense, chaos behaves like weather. Individual droplets are a lost cause. Storm tracks are fair game. None of this needs fantasy butterflies flapping hurricanes. Celestial chaos is modest forces, correctly timed, acting inside architectures predisposed to amplify them. Resonances sculpt the resonant. Secular drifts turn the slow knobs. Weak encounters throw dice. And the system, taken as a whole, evolves in ways that are unpredictable in detail, yet legible in bulk. Next, we'll bring the consequences home. How small, slow tweaks in Earth's orbital elements modulate climate over tens to hundreds of thousands of years, and why even a flashy interstellar visitor is a poor candidate for touching those dials. Climate knobs exist, but 3I has the arm strength of a T-Rex trying to change the thermostat. Earth's long-term climate is exquisitely sensitive to where and how sunlight lands, and the controls aren't hidden. 3 slow-motion dials called eccentricity, obliquity, and precession. Turn them a little, and you don't conjure snow overnight. You refocus the seasons, then let oceans, ice sheets, and the carbon cycle do the heavy lifting. Over tens to hundreds of thousands of years, those quiet adjustments can tip us into or out of ice ages. The question is whether a flashy interstellar visitor, like 3IATLAS, could bump any of those dials. Spoiler, the only thing it can reliably adjust is our telescope schedule. Start with eccentricity, the shape of Earth's path around the Sun. It oscillates from almost circular to slightly oval on roughly 100,000 and 400,000 year beats. The total annual sunlight barely changes, but the timing and intensity do. When the orbit is a touch stretchier, one hemisphere's summer can happen nearer perihelion, a bit closer to the Sun, juicing seasonal contrast there. Ice sheets care less about the yearly average and more about whether summers get warm enough for long enough to erase winter's accumulation. Eccentricity doesn't act alone, but it sets the stage for drama by making the when of heat delivery matter more. Obliquity is the tilt of Earth's spin axis. Nudge that tilt, which meanders by a couple of degrees over 41,000 years, and you rewrite the latitudinal budget. Higher tilt dials up polar summers and winters alike, big swings at high latitudes, while slightly easing the tropics. Lower tilt does the opposite, calming the poles and feeding mid-latitude snow survival. This is where ice albedo feedback enters like an accountant who loves multipliers. More snow and ice reflect more sunlight, cooling things further, which preserves more snow and ice. Small shove, big echo. Precession is the slow wobble of Earth's spin axis, combined with the ellipse's orientation, reshuffling which hemisphere points sunward at perihelion. Its dominant rhythm is 19 to 23,000 years. Precession is the monsoon whisperer. By moving peak summer insolation north or south at just the right time in the year, it can strengthen or weaken continental heating gradients that power seasonal rains. The oceans, vast heat sinks with the personality of a stubborn cat, modulate the response and add lags. Still, stack a favorable precession phase atop a helpful tilt, and you can boost or mute regional climates in ways that shepherd ice margins over millennia. None of these dials acts in isolation, and none guarantees a climate outcome. The system is a conversation among insolation patterns, ice dynamics, greenhouse gases, and ocean circulation. For example, stronger summer sunshine at high northern latitudes can shrink ice, darken the surface, warm the region further, and release CO2 from oceans that are mixing differently, a positive feedback loop that pays dividends over thousands of summers. Reverse the conditions, and you can seed growth of ice sheets that chill the planet and draw down CO2. The hallmark is pacing, slow build-ups, delayed peaks, and climate changes that look like staircases rather than switch flips. Could 3IATLAS give any of these dials a noticeable flick? To matter, It would have to alter Earth's orbital elements by amounts comparable to the natural cycles, or at least shift their phase in a way that persists. That takes a coherent gravitational nudge coupled to Earth's motion, not a brief cameo near the Sun. A kilometer-scale visitor blasting through on a hyperbolic path interacts with Earth's orbit, mostly by existing in the same universe, unless it threads an absurdly close pass. Astronomically rare, it cannot hand Earth a measurable change in semi-major axis, eccentricity, or inclination. Jupiter and Saturn already dominate those secular tunes. Earth is a middle voice in their choir, not a soloist taking outside requests. What about indirect routes, like slightly altering the distribution of small bodies, whose later impacts or dust loads tweak climate? Romantic, but numerically starved. A one-off interstellar comet can't reorganize asteroid or Kuiper belt resonances, and any dust it sheds is a rounding error alongside the perpetually replenished zodiacal cloud. Even a hypothetical microkick to Earth's precession rate would need to compete with the stabilizing leverage of the Moon, whose gravitational partnership damps wild swings in tilt. If the climate knobs sit behind glass, the Moon is the glass. Another reason 3I's odds are thin: climate's inertia. Ice sheets take centuries to millennia to respond fully. Oceans store and ferry heat on similar timelines. A transient perturbation must be either large or resonant to leave a trace. Large is off the table. Resonant requires matching Earth's slow precession or tilt cycles with a sustained torque. A flyby delivering minutes of extra gravity at interplanetary speed is a cymbal crash in a symphony, scored for cellos. It's worth flipping the script. If you did somehow shift Earth's orbital elements by a hair, would we notice soon? Probably not, as weather. The signal would creep in through altered seasonal insolation patterns, nudging snow lines or monsoons by small amounts that only turn into big stories after feedbacks integrate them for ages. Paleoclimate reconstructions see these patterns because rocks and ice are patient archivists. Today's thermometers, living on human timescales, mostly hear the percussion of greenhouse gases and aerosols, all of which leaves 3I with a more realistic and still exciting job description. It's not a thermostat ninja, it's a courier. Its volatiles and dust tell us how other planetary systems build their comets, which in turn informs our understanding of early Earth. What ingredients rained down, what catalysts might have wandered in, what climate-relevant molecules roam interstellar space. That's a lot of value without pretending the visitor can tweak Earth's seasons on its way to somewhere else. So yes, the climate knobs are real, and they matter profoundly, but they're slow, heavy, and mostly operated by celestial mechanics internal to our system, with the Moon as a stabilizing supervisor and the giant planets as the background rhythm section. 3IATLAS is a fascinating solo, not the band leader. Next up, we hand the mic to the bouncer at the door. Jupiter's role in deflecting, capturing, or ejecting visitors, and how its sheer mass makes it the reason most interlopers don't stay for an encore. Once flagged, speed run the characterization. A flyby, you understand, is a non-story. A mystery is what keeps people up. Triaging a fresh object means rapid astrometry. Nail the orbit. Photometry, light curve, hints at shape and spin. Spectra, what's it made of? And coma monitoring, is it outgassing? Automate the handoff. When a candidate looks interstellar, high hyperbolic excess, bots should ping priority queues at major facilities, pre-generate exposure plans, and schedule follow-ups before the press release writes itself. Add small, agile telescopes armed with fast spectrographs to fill in the gaps while the giants slew. It's triage as choreography. Decision-making needs plumbing, not poetry. 2 global channels already exist for impact risks. One for information sharing and one for strategy discussion. Strengthen both by committing to common playbooks and routine drills. That means standardized alert levels, red team exercises that inject fake but plausible objects into the pipeline, and tabletop simulations where policy, science, and emergency management practice talking to each other before microphones arrive. The win condition is simple. When the day comes, nobody asks who's in charge, because that question was retired years ago. Planetary defense overlaps with space traffic management and science in delicious ways. The same pipelines that issue hazard alerts can also feed mission planners looking for targets of opportunity. If an interstellar object appears with a geometry that allows a quick recon pass, a standing ISO task force should be able to greenlight a micro-mission in hours, not months. Think rideshare CubeSats with off-the-shelf cameras and mass spectrometers, stashed at depots in cislunar space, or Lagrange points waiting for a go code. You won't deflect an ISO, but you can meet it, sniff it, and wave. For big bound threats, the ones that actually merit moving, our tool belt needs both gentle hands and firm taps. Kinetic impactors, the shove it with a battering ram option, prove we can transfer momentum predictably. Gravity tractors, park a heavy spacecraft nearby, and let mutual gravity tug for years. Show we can be patient when time permits. On the bleeding edge, ion beam shepherds and laser ablation promise thrust without touching. Ion engines aim a plume at the asteroid to push it. Laser arrays vaporize millimeters of surface, turning rock into exhaust for a controllable thrust vector. None of these are for 3I-class visitors screaming through on a one-week tour. They're for the lumbering, bound objects we discovered decades early. Every deflection architecture begs for logistics. You want options pre-baked, not invented on live TV. That means keeping a small fleet of Tug-class spacecraft at high readiness standard buses, standardized interfaces, modular payload bays for either kinetic noses, ion thrusters with generous propellant, or laser modules that scale by number. Store propellant where it's easy to reach. Park assets at energetically sweet spots, like Earth-Moon L1, L2, so they can sprint either inward or outward with minimal delay. Build an O-berth kit, stages and heat shields that let a mission dive close to the sun for a high-energy burn when you need interplanetary delta V on short notice. You hope to never need any of this. You will sleep better because you do. Data hygiene is defense. Keep ephemerides honest with constant cross-calibration. Radar ranging when possible, laser ranging to cooperative targets, and a global open pipeline for astrometry that incorporates uncertainty properly. No heroic fits to noisy arcs. Publish risk corridors with clear, conservative confidence bands, so downstream users, satellite operators, aviation authorities, and the public don't mistake crisp graphics for certainty. When you communicate risk, use frequencies people understand. 1 in X per year, not sigma soup. Education and citizen science convert curiosity into coverage. Small telescopes with decent CCDs can contribute real astrometry if they follow strict calibration recipes. Give them those recipes. Offer certified training that turns amateurs into auxiliary observers during alert windows. Meanwhile, equip journalists with pre-built explainers, unit converters, and an embargoed Q&A, so the first wave of stories gets the verbs right. Panic is bad engineering. International law lags hardware. Begin now on norms for test deflections, where to aim momentum, so you don't export risk, debris responsibility, who pays if a kinetic impact sheds fragments into valuable orbits, and dual-use transparency. A laser array that can ablate a rock can also dazzle a satellite. Build inspection protocols and data-sharing commitments before a real event forces the negotiation under a deadline. Treat deflection capability like nuclear safety. Trust, verify, and publish. Finally, embrace fast reconnaissance for ISOs. We won't redirect them, but we can learn faster. Park a few solar electric interceptor buses on standby trajectories with flexible delta V margins, paired with tiny impactor cameras for flash chemistry. Add sundiver solar sails that can brake or sprint as needed. When the alert sounds, you don't design, you launch. If the whole list feels dull, good, safety is made of yawn-worthy habits that endure. The payoff is a world where a surprising visitor becomes a science festival, not an emergency meeting. Next, we cash in that festival. Even when a visitor can't budge anything, it can spill elemental secrets from another star. We'll unpack the science jackpot, what 3I type objects teach us about planet formation, chemistry, and the early recipes that might have flavored worlds like ours. Even if it can't push us, it can still spill cosmic tea. A visitor like 3IATLAS is a courier from a different planetary nursery, and couriers are valuable even when they don't move furniture. The prize isn't a new orbit for Earth, it's a new page of chemical, physical, and statistical clues about how other systems build worlds, bake ices, and toss their leftovers into interstellar space. Start with chemistry, the gossip column of the cosmos. A comet's coma is a mobile lab. Sunlight heats the nucleus, ices sublimate, and the gas drags dust grains outward, where telescopes can dissect the light. Optical spectra chase familiar radicals, CN, C2, C3, while infrared and millimeter bands go shopping for CO, CO2, H2O, HCN, CH3, OH, and friends. The relative strengths of these lines sketch a shopping list of volatiles. If 3IATLAS shows an unusual CO-CO2 ratio, for instance, that hints at how cold its birth disk was and how far from its star the object accreted. Chemistry is a time machine disguised as a barcode. Then come isotopes, the dialects of elements. Deuterium to hydrogen, DH in water, is a classic thermometer. High DH points to formation in colder, outer regions. Lower DH suggests warmer neighborhoods or later processing. Ratios like 15N and Fokin C tune the backstory further. Were organics built under UV-rich conditions? Did grains see cosmic ray spallation? Even oxygen's triple isotope quirks can flag which photochemical pathways stamped the ice. Short version: two water molecules can look identical in chemistry, but scream different childhoods in isotopes. Science loves loud childhoods. Dust grains are the archaeological layer. Comet dust scatters light with a wavelength-dependent color. Measure that color, and you infer grain sizes and compositions. Polarimetry, how the coma's scattered light is polarized, adds texture. Fluffy aggregates polarize differently than compact silicate grains. Find crystalline silicates in the mix, and you've caught evidence for high-temperature processing near the star, followed by radial transport outward. Find mostly amorphous stuff, and the recipe stayed cold and simple. Either way, you're reading a sedimentary record that formed long before the nucleus ever went rogue. Microscopes are great. In astronomy, we do microscopes with photons. Spin states and shapes also tell tales. A nucleus's light curve, how its brightness rises and falls as it rotates, reveals whether it's a tidy ellipsoid, a contact binary, or an irregular potato with opinions. Rotation rates that change over days betray jet torques. Sunlight warms a patch, gas vents, and the comet experiences a tiny thruster effect. Catch that time series, and you've not only mapped where the vents are likely to be, you've measured the mechanical strength of an alien snowball. Spacecraft engineers call that material properties. Poets call it how crunchy the cosmic gelato is. Formation clues live at larger scales too. The mere existence of 3IATLAS informs planet formation efficiency. Every interstellar object is a census point for ejection during planet building, evidence that young giant planets or chains of super-Earths scattered planetesimals with gusto. Count enough ISOs and you constrain how often disks spawn big bodies early, how violent those early years are, and which architectures fling more debris. It's galactic demography via crumbs. Kinetics matters as well. The inbound speed and incoming direction, mapped against the local standard of rest, hint at dynamical processes in the visitor's home neighborhood. Was it casually unbound by a developing giant planet, or ejected at speed by resonant chaos in a compact chain? If the velocity aligns with known stellar streams, you've got a breadcrumb trail toward the kind of system it came from. Interstellar objects don't carry return addresses, but they sometimes leave smudges on the envelope. We also learn by what we don't see. If 3IATLAS shows weak water but strong CO, you've met a nucleus with shallow H2O, or one whose water hides beneath a crust, an evolved surface that baked off its most volatile layers during prior star flybys. If dust production is meager, yet the gas lines sing, the grains may be larger, stickier, or locked under a rind. Non-detections are not empty. They fence in the parameter space and tell modelers politely to stop drawing dragons there. Multi-wavelength campaigns are the secret sauce. Pair a big optical survey that pins down the orbit with infrared spectra for molecules, millimeter arrays for cold gas mapping, and ultraviolet snapshots for hot, fresh emissions near the nucleus. Add polarimetry to read grain structure and time series photometry to catch jet-driven spin changes. Toss in a couple of radar pings if geometry permits, and you've triangulated size, albedo, roughness, and activity with embarrassing precision, all while the object sails on. We didn't even touch it. Becomes a flex. Could we ever touch one? Interstellar sample return is hard. The objects are fast and fleeting, but not impossible in principle. Short of that, dust capture in Earth's upper atmosphere during close passes might snag a few grains, their entry speeds branded by hyperbolic approach. Laboratory isotopic forensics on a true ISO grain would be jackpot times jackpot. A pre-solar fingerprint you can weigh. Until then, remote sensing is the name of the game, and modern observatories are very good at it. Telescopes are just very large, very polite pickpockets. Even a failure to move us is success for understanding us. Comparing isochemistry to solar system comets tests whether our disk was weird or ordinary. If organics look familiar, life's raw ingredients are probably universal cafeteria food. If they're wildly different, we've learned that planet making explores a broader recipe book than our sample of ones suggested. Either way, the narrative sharpens. Life elsewhere is either playing with the same pantry or improvising with equally rich substitutes. Both outcomes are thrilling. Science is greedy that way. And finally, there's the culture of readiness. Each ISO forces our networks to practice rapid identification, coordinated follow-up, and clean data fusion. We get better at choreography every time. The payoff isn't just one object story. It's a faster, smarter community that can pivot the next time the universe tosses us a curveball. Practice doesn't make perfect, but it does make publishable. So yes, 3IATLAS won't steer the solar system, but it will steer our understanding of chemistry, of origins, of how common our path might be in a galaxy of planetary experiments. The tea is hot, even if the push is not. Next, we'll zoom out from lab notes to perspective, why interstellar traffic humbles our center stage instincts, and why curiosity, more than certainty, keeps a species afloat in a restless galaxy. Earth is a small boat on a big ocean. Bring oars and questions. Interstellar traffic makes this painfully, beautifully clear. Once you've watched a stranger from another star whistle through the sky and ignore our planetary dramas, you realize the universe did not reserve a VIP section for us. We're the balcony seats in a theater with no walls. That's not a demotion. It's an invitation. The first perspective shift is scale. We're good at measuring things we can hold, not distances we can barely imagine. A visitor like 3IATLAS compresses the galactic into the local. Something born under a different sun sweeps through our backyard, declaring that far away is a temporary condition, and somewhere else occasionally shows up unannounced. It shrinks the psychological gap between out there and right here. When the sky delivers a postmarked object to your doorstep, the address book of reality gets longer. Humility follows quickly. Our maps of orbits, of chemistry, of how planets assemble, are patchwork quilts. They're good enough to sleep under and full of seams if you look closely. Each interstellar guest tugs a thread. Are we typical or weird? Are our watery rocks universal, or are we a lucky draw? The honest answer lives somewhere between probably not special and uniquely ourselves, the way every beach is made of ordinary sand arranged in a one-of-a-kind curve. Humility means letting data lead and resisting the urge to grade the cosmos on a curve, with Earth as the answer key. Curiosity, though, is humility's co-pilot. It asks better questions precisely because we're not at the center. If comets written in other alphabets keep visiting, we learn to read them. If their isotopes speak with a different accent, we practice listening. The mindset shifts from prove we matter to understand what is. That's a healthier engine for a species that wants to last. Less ego, more puzzle solving. The universe rewards curiosity with more universe. There's a social technology hidden in this too. Cooperation. It takes coordination to spot, track, and interpret a fast interstellar object. No single telescope, no single country, no single clever team can do it alone. The good stories, the ones with spectra, time series, and a stitched-together arc from discovery to goodbye, come from networks that share that habit scales. If we can collaborate on studying a wandering snowball, we can collaborate on bigger projects. Planetary defense, climate stewardship, and the kind of patient science that pays off after election cycles forget your name. Interstellar visitors also recalibrate our sense of risk and meaning. It's easy to build apocalypses out of small objects because they move fast and look dramatic, but the sober view says they're lessons, not threats. The truly existential hazards, our own emissions, our geopolitical tantrums, the slow erosion of shared facts, don't streak across the sky with a tail. They creep. A comet from another star doesn't erase those troubles. It puts them in context. We live on a mobile platform in a dynamic galaxy. Maintaining the boat matters more than narrating the waves. Wonder survives all that practicality, and it should. Awe isn't a soft luxury. It's cognitive fuel. A species that can feel small and still want to learn is a species that can keep going. There's a reason the first photograph of Earth from deep space did more for environmentalism than 1,000 memos. Seeing yourself as a speck is not demoralizing when the speck is surrounded by a canvas worth exploring. Awe loads the oars. Curiosity picks a direction. Time is the last teacher here. We obsess over short intervals, fiscal quarters, news cycles, the wait between seasons of a show. The galaxy runs on patience. A single interstellar pass is a heartbeat in a life measured in billions of years. The lesson isn't to ignore the present, it's to braid timelines, to do the urgent work, keep people fed, healthy, informed, while investing in the long work, build instruments, collect baselines, plan missions, whose payoff our grandchildren will cash. Civilization is a relay, not a sprint. Visitors from other suns are the baton toss that reminds us to keep our hands open. Values sneak in at the edges of these choices. If you believe knowledge is a public good, you build open catalogues. If you believe borders are the primary unit of meaning, you hoard ephemerides like treasure. If you believe the future has rights, you design infrastructure that outlives your resume. None of those commitments are dictated by physics. They are, however, illuminated by it. The sky doesn't care who claims ownership. It cares whether we look up often and carefully enough to learn something true. There's also grace in ignorance. Not every question about an interstellar object can be answered before it's gone. Accepting that, admitting the limits of what tonight's telescopes can say, keeps science honest. It's okay to wave goodbye with a list of mysteries intact. Letting the unknown remain unknown for a while is not failure. It's an IOU to the future, to build better instruments and train better questions. Our neighborhood philosophy, then, is simple. We are passengers and caretakers on a moving platform. We share a sky with wanderers that prove the galaxy is busy and indifferent. And that indifference is our freedom. We can choose to be curious without asking the cosmos for permission. The ground rules are clear. Measure well, share data, design for the long term, and cultivate a public that finds joy in accurate stories about reality. Everything else is ornament. So as the next interstellar courier heralds itself with a faint, fast smear on a survey image, we get to decide, again, who we are when the universe knocks. Anxious owners of a fragile stage, or delighted tenants who keep a tidy, well-instrumented porch. I'm rooting for the porch. Next, we'll wrap the saga. We'll harmonize all the threads from flyby mechanics to galactic tides, and close the counterfactual cleanly on why a meaningful orbit change is vanishingly unlikely, which tiny signatures might still appear, and why keeping tabs on cosmic couch surfers is worth every late night. The solar system isn't easy to nudge. Think sumo wrestler on ice skates with very good balance. That's the punchline to our long what if, but it's worth stitching the reasons together cleanly, so the logic stands on its own legs. Start with mass and momentum. A visitor like 3IATLAS is small, fast, and temporary. Small means it doesn't carry much momentum compared with planets or the sun. Fast means it spends almost no time in the zones where gravity could actually curl its path into something dramatic. Temporary means the interaction is a cameo, not a residency. The result is an encounter that alters its fate far more than ours. Next comes bookkeeping. Internal tugs shuffle motion among members of a family, but don't give the family a new trajectory through the wider world. To alter the solar system's motion relative to the galaxy, an outsider would need to contribute momentum on a scale that competes with the mass of the sun plus planets. A kilometer-class object is a whisper next to that choir. Even the most acrobatic flyby merely edits the visitor's exit vector. The combined ledger of sun and planets registers the exchange as a rounding error and carries on. Structure is another defense. Our planetary layout isn't a precarious stack of plates. It's a set of orbits spaced widely enough and buffered by deep wells of angular momentum that small impromptu taps don't cascade. Resonances carve channels and create exclusions, but those rhythms require persistence to move the needle. A single dash through the inner system can't pump those long-period modes coherently. It's percussion in a symphony written for strings. Could there be edge cases? Yes, but they're still modest. A deep brush past a giant planet might shred a fragile nucleus, spray fragments on a variety of tracks, and raise the odds that one or two pieces wander into sunlight later, as brighter comets. You might also dislodge a few small bodies that were loitering near resonance borders, nudging them onto different multi-orbit journeys. These are footnotes you'd need patience to find, changes in counts at the percent level, altered phase for a handful of long shots, a night sky with a bonus act years hence. None of them moves continents. At best, they rescore a few bars in the background. So if big is off the table, what tiny signatures could appear, and how would we catch them? First, local orbit tweaks in the minute category. A small asteroid's parameters slightly shifted after a coincidental near pass. You don't detect that by watching one rock. You see it statistically. When ensemble fits to many objects, report a faint but consistent redistribution. Second, ephemeral barycentric wrinkles. During the days, a visitor is nearby. The combined center of mass includes it. So the sun's reflex trace grows a short extra loop. That tiny kink vanishes when the guest leaves, but it leaves timing crumbs across our measurement systems. Pulsar clocks, long baseline astrometry, and deep space radio links are allergic to inconsistencies. If the nudge were big enough to care about, you'd see a coordinated, time-localized improvement in residuals when the model includes the visitor's pull. Third, dust gossip, a bit more fine material along the object's trail, slightly altering the brightness structure of the inner dust bands for a while before collisions and radiation forces erase the note. Everything above sits beneath the threshold of public drama. That's okay, because the serious payoffs live elsewhere. Tracking, chemistry, and practice. Tracking matters because the universe does surprises on its own schedule. Early detection buys time to take spectra, while the object is still gassy, to schedule radar or infrared passes at the sweet spots, and if geometry smiles, to propose a fast flyby from a platform already idling with spare propellant. A planetary system that can choreograph an observing campaign in hours isn't panicking, it's warmed up. Chemistry matters because it tells us how other disks cook. Each interstellar object is a data point on the diversity of planetary kitchens. What ices survive, what organics assemble, which isotopic accents show up in the water and carbon chains. The headline from a well-studied visitor won't read orbit changed. It will read recipe found. That's the kind of sentence that refines our theories of planet formation and, by extension, informs where and how to look for habitable zones that taste like ours. Practice matters most because it compounds. Every alert drills the pipelines: survey detection, orbit determination, community triage, telescope handoffs, and, when warranted, mission concepts that can hitch a ride or sprint from standby. The more we do it, the less friction we carry next time. That muscle carries over to non-interstellar threats too. The same infrastructure that clocks a fast outsider will clock a local object on an awkward future path. And the same calm choreography will turn a potential scare into a competent shrug. There's also a philosophical dividend. Calling a thing harmless and still studying it hard is a cultural choice. It says we value understanding even when fear isn't involved. That's a healthy reflex for a species that wants to persist. It keeps the spotlight on curiosity instead of crisis, on measurement instead of myth. And when a day arrives that does carry urgency, we'll have a generation of scientists, engineers, communicators, and decision-makers who have rehearsed together so often that the hard parts feel familiar. So our final what if lands softly. If a visitor like 3IATLAS sweeps through, the solar system stays the sturdy skater it's always been. The signatures left behind are the kind you read with patient instruments and long spreadsheets, tiny redistributions, faint timing harmonies, extra dust sunlight can play with for a season. The reasons rest on mass, momentum, architecture, and time, boring words that quietly keep you safe. But boring isn't a verdict, it's an opportunity. It frees us to ask better questions and build better tools. Keep watching, keep cataloging, keep the porch light on, and the spectrograph warm. The visitors won't move us, but they will move our understanding, one carefully measured whisper at a time. And that's the series. Next project, we can dive somewhere new. Maybe worlds under ice, or the first atmospheres of young exoplanets. Any place the questions are sharp and the answers still just out of reach.